1, 2, 3. Yeah! Thermodynamic processes are the different ways heat and energy can be transferred in a system. But before we get started, let's talk about how to properly produce a graph. Graphs are always labeled by the y value versus the x value. Of course, in science, we don't call it y and x. Instead, we call it the dependent variable versus the independent variable. So when we're trying to plot out a pressure-volume graph, we're plotting out one where pressure is the dependent variable, volume is the independent variable. Now, if we assume that temperature is fixed as well as the quantity of molecules remain the same, if we isolate for P, we find out that pressure and volume are inversely correlated. In other words, as volume increases, pressure decreases. So when we plot the graph, it should look something like this. Now, this is at room temperature. If we increase the temperature of our system, we'll notice the curve will look more like this. And if we increase it even more, you'll notice that the curve moves further to the top right. So that's the trend that you'll see in a pressure-volume graph. As temperature increases, the curve will shift to the top right. Now, these family of curves actually have a name associated with it. They are known as the isotherms. In other words, as long as you keep the temperature the same, this is the correlation you'll see between pressure and volume. Now, there are 4 different ways how energy and work can be transferred in a system, and that's what we'll be discussing about in today's episode. When you hear the root word baric, you might think of a barometer. In fact, that's what an isobaric process is. It's one where the pressure remains the same. And if you observe the area underneath the graph, it does have a significant meaning. Let's check it out. As you may know, units must always work out. So since the area underneath this graph is a measurement of height times base, and height is a measurement of pressure, and the base is a measurement of volume, then you have a unit of pascals times meters cubed. A pascal can also be rewritten as newtons per meter squared. And when you divide meters cubed by meters squared, you just get meters. And a newton times a meter gives you a joule. So the area underneath a pressure-volume graph always tells you work. Now, this formula here sometimes has a plus symbol, sometimes it has a minus symbol. In this situation here, it's a work performed by the surroundings onto the system. So it's like a big person trying to squish a tennis ball. So work will be positive when work is done onto the system by its surroundings, and work will be negative when work is done by the system onto the surroundings. On the AP exam, this is written as work is equal to negative pressure times volume, and this is the work done onto a gas. Here's an example. How much work does it take to compress 10 milliliters gas down to 5 milliliters at STP? STP stands for standard temperature and pressure. Remember that volume needs to be measured in meters cubed, and currently we have the volume measured in milliliters. 10 milliliters also translates into 10 centimeters cubed. And as you may know, there are 100 centimeters in 1 meter. So to convert centimeters cubed into meters cubed, you must divide the number by 100, 3 times, 1 for each dimension. So 10 centimeters cubed divided by 100, divided by 100, divided by yet another 100, gives you a very small number. The same is also true when you convert 5 milliliters into cubic meters. At standard temperature and pressure, the pressure is at 101.3 kilopascals. And when you work through this, you'll find out that you have a positive value. This is because your final volume is less than your initial volume, and you are performing positive work on compressing the gas. Work can also be perceived from the gas's perspective, where if the gas is allowed to expand, then the gas is able to perform positive work. And if somebody is squishing on the gas and the gas is not strong enough to expand and it compresses, then the gas is performing negative work. So that's the confusing thing about this formula here. Sometimes there's a plus sign in front, sometimes there's a minus sign in front. You have to think about who's the person who's performing the work. Is it the gas, also known as the system, or is it somebody from outside, called the surroundings? Let's go through this mathematical example. Whenever you heat up a gas, it has a tendency to want to expand until the pressure inside matches up with the pressure outside. We're assuming that the piston and its contents are massless. Let's say that we heat up 1 gram of water into 1.67 liters of steam. We boil it at standard atmospheric pressure. So the pressure inside the container wants to match up with the pressure outside as the water is expanding. And we're trying to determine what's the work done by the water when it vaporizes. So this time around, we need to take the formula and treat it as positive, as we're finding out the work conducted by the gas onto its surroundings. and the final answer should be positive. The next part you're not responsible for the AP exam, but let's work it out anyways so that you have a better understanding of what's happening here. As you may recall from a previous video, the change in internal energy is equal to heat minus work conducted onto the surroundings. As we're heating up the gas, it's gaining internal energy. But since this is a change from water into steam, it's a change of energy in the form of latent heat. An isochoric process is also known as an isovolumetric process. In other words, the volume remains the same. You'll notice over here that there's no area underneath the graph. And since there's no area underneath the graph, work is equal to 0. You can also see this mathematically. Since there's no change in volume, work is equal to 0. It is possible for the internal energy to increase instead. A good example of this is if you take a can filled up with gas and you heat it up. The molecules start moving faster and faster. However, because there's no change in distance, because there's no increase in volume, the gas does not do any work. Instead, the pressure just gradually increases in the can, and you hope that it doesn't explode. The stuff that's written in blue, you don't really need to worry about for the AP exam, but again, just for good measure, let's go through the calculations anyways. What is the change in internal energy when you heat up carbon dioxide from 25 degrees Celsius to 30 degrees Celsius? Well, you'll know that the change in internal energy is the heat gained by the gas because it's being heated up. An isothermal process is one where the temperature remains fixed. But keep this in mind. In general, whenever you compress a gas, the temperature of the gas wants to increase. And when you let a gas expand, in general, the temperature of the gas wants to decrease. However, in an isothermal process, you're regulating the temperature so that there is no change in temperature. So how does it regulate this? Well, it has to either steal heat from the environment or dump heat out into the environment. To find out the area underneath this graph, you'll have to actually do a bit of calculus. There is something known as the antiderivative or the integral, and that's how you find out the area underneath this curve. Again, this is beyond what you need to know for the AP exam, but it's nice to know where this formula comes from. All you really need to worry about for the AP exam is that as long as the temperature remains fixed, the change in internal energy is equal to 0 joules. And this is accomplished by having a huge heat sink surrounding your system. Typically, this experiment is conducted by placing your piston inside water. Since water is an excellent heat sink, it'll actually regulate and moderate the temperature so that it won't fluctuate. Just for fun, here's a calculation example. As you're allowing this gas to compress, you have to dump the heat into the water. And the question is, what is the final volume given this particular situation? The more challenging part of this calculation is that you'll need to know the complementary function for ln, which is the natural number E. So you isolate for VF, and you find out that the volume of the gas is now decreased down to 35 milliliters. Now, if heat wasn't removed from the system, the volume of the gas would actually be slightly higher because of the elevated pressure. But what if a system cannot take in any heat from its surroundings, nor can it dump its heat back outside? Well, then we have something known as an adiabatic process. In an adiabatic process, the gas will either lose temperature when it expands, or it will gain temperature when it's compressed. We find out mathematically that the work conducted onto the gas results in a change in internal energy. Now, you really don't need to worry about anything below the blue bar, but this is the most fascinating part about thermodynamics. In your textbook, you'll see this formula here. And before you continue onwards, you have to think about the gas that you're breathing in right now. As you may know, the atmospheric air is comprised of approximately 78% nitrogen and 21% oxygen. So in other words, almost 99% of the gas that we breathe in is diatomic. And that's why we choose 7/5 for our value of gamma. So if you take this formula, as well as the ideal gas formula, and you sub it in, and rearrange and simplify, you create a brand new expression. And in this expression here, you can see the change in temperature on the gas when you compress it and when you expand it. Where in general, as you compress the gas and the final volume is less than the initial volume, your temperature quickly rises. And if you allow the gas to expand very quickly, the temperature of the gas will then suddenly drop. What I have here is a pop can that I'm increasing the pressure inside up to about 40 psi. The standard atmospheric pressure is somewhere around 17 psi. Now, when I quickly allow the gas to expand, you'll notice that condensation forms inside the container. This is due to the sudden drop in internal temperature, where it allows the water vapor to suddenly condense, thus forming a cloud. Now, the opposite can be true as well. At the beginning of this video, you may have noticed that I quickly compressed a piston and it caused a lint of cotton to catch on fire. As you compress a gas, there is a change in internal energy, and if the gas can't dump the heat into its surroundings, then the temperature of the gas will then increase. So let's go through the math of this. So a former student of mine actually gave one of these to me as a gift. And I have to do this process very rapidly because I need to compress the gas from 10 milliliters down to 1 milliliter, hoping that I don't warm up the piston. Because if I do, the piston will behave as a heat sink, then I won't be able to ignite the cotton. So we use the formula that was quickly derived in the previous slide, and we sub in the corresponding values. We find out that the final temperature works out to 746 Kelvin, which is roughly 473 degrees Celsius. And if you look it up, the flashpoint temperature of cotton to ignite is roughly around 400 degrees Celsius. So now we have covered the 4 different thermodynamic processes. An isobaric process is one where pressure remains constant, and you have to decide whether to use a plus sign or a minus sign. Think carefully about the direction of energy flow when you're solving these type of problems. As for an isochoric process, the volume remains constant. And because there's no change in volume, no work is conducted to the surroundings, nor is any work from the surroundings being processed onto the gas. An isothermal process is one where the temperature remains fixed. Keep in mind the only way you can regulate temperature by expanding or compressing a gas is by dumping that heat into its surroundings or by taking the heat from the surroundings into the gas. And lastly, if the gas cannot take in any heat nor dump its heat, then the gas has no choice but to heat up itself, and that's what an adiabatic process is. An ideal gas is trapped in a cylinder with a piston that can move up and down. The gas is initially at room temperature and occupies 1 cubic meter of space. The piston is in its equilibrium position. What this means is that the air pressure inside the piston matches up with the air pressure outside of the piston. A mild heat source is then applied and the gas is slowly warmed up to 350 Kelvin, where the piston moves up to allow the gas to expand. Once the new temperature is reached, the volume of the gas is now 2 cubic meters. What type of process is this? Since the gas is allowed to expand, where the internal pressure matches up with the external pressure, this is an isobaric expansion. The piston is now locked in its new position, and the gas is allowed to cool down to room temperature. Again, when the temperature of the molecules decrease, the molecules move a lot slower. It produces a lot less pressure. So the pressure inside this container will then be less than the pressure outside. However, since the volume has not changed in this container, it is classified as an isochoric process, or an isovolumetric process. Finally, when the room temperature is reached, the piston is pushed back manually, but very slowly, so that the gas inside is equal to the gas outside. So if we're trying to keep the temperature the same, this is classified as an isothermal process. Now, as the gas is compressed, it needs to liberate the heat, so it's going to pass the heat onto its environment. We assume that the environment is super huge, so that even though it should technically gain in temperature, it doesn't overall because it's so massively huge. Here's a good AP exam question. Let's say that we compress a gas, but we keep the temperature the same. Which of the following are correct? Well, we know that we are performing positive work in compressing a gas, so C and D are incorrect. And as you compress a gas, in general, its temperature wants to increase, as you are confining the gas molecules into a smaller space, and they bounce off each other far more frequently. However, since this is an isothermal process, that means that the temperature must remain the same, and the only way for it to do that is by dumping the heat into its environment. That's why B is the correct answer. There will be a few AP questions where the only way for you to receive that 1 full mark, you have to select the 2 correct answers. So a fixed amount of gas is kept in a container of fixed volume. The absolute pressure of the gas is plotted as a function of its temperature in degrees Celsius. Which of the following are the properties of a best fit curve to the data? At the beginning of this video, we went through an exercise of plotting out graphs we have yet to see. In this case, we're plotting out a graph that's a relationship between pressure and temperature. Taking a look at the ideal gas equation and isolating for pressure, we find out that pressure and temperature are a linear correlation. The only thing that isolates it is a corresponding slope. Now, does this slope necessarily have to pass through the origin? Well, no. And the reason why is because this temperature here is not measured in degrees Celsius. It's measured in Kelvin. So it is possible for the pressure to drop down to zero, but definitely not at 0 degrees Celsius. After all, if it did drop at 0 degrees Celsius, then the air in the atmosphere will solidify and drop down to the Earth. Our atmosphere will then disappear. Lastly, you'll notice that this is a positive correlation, so as temperature increases, pressure must increase, so it's impossible for the pressure to drop down to zero when temperature reaches infinity. I hope you find this video useful in your review. Stay tuned for our last episode on thermodynamics.